When we studied the electric field and displacement inside and outside dielectric materials, we mentioned that the boundary conditions on these field quantities over surfaces and interfaces are important to provide the complete description of these fields. If two homogeneous and isotropic media with different dielectric constants are in contact with each other over an interface which can be considered flat in a small environment, then we assume that the vectors of the electric field E and the electric displacement D change at the interface when we cross the interface. Let E1 and E2 denote the vectors of the electric field in the two media with the absolute dielectric constants epsilon1 and epsilon2 with a boundary interface separating them. Similarly, we denote the vectors of the electric displacement by D1 and D2 in the two dissimilar dielectrics. At a given point of the boundary interface with the surface normal n, we can decompose the electric field strength and the displacement vector into tangential and normal components with respect to a plane approximating the boundary in a small vicinity about the normal vector n. The task is to determine the boundary conditions for the tangential and normal components of these vector fields over this small flat boundary surface area. In order to do this, we apply the second Maxwell equation in electrostatics telling us that the electric field is curl-free, that is the line integral of the field strength E of an electrostatics field along any closed contour is equal to 0. Now we determine the line integral of the electric field E along a closed contour defined by the rectangle with the corner points A1, B1, B2, and A2 enclosing the boundary interface between the dissimilar dielectrics such that its longer sides are parallel with the interface in a small vicinity where the boundary can be considered flat. Then the line integral of the field strength E along the rectangle can be broken up to four line integrals along the sides of the rectangle, that is the line integrals along the straight sections between the points A1 and B1, between the points B1 and B2, between the points B2 and A2, and between the points A2 and A1. For the curl-free electrostatics field, the algebraic sum of these line integrals of the field must vanish. Since the closed contour along which we determine the line integral of the field strength is arbitrary, we can deform the rectangle such that its height tends to 0. That is the corner points A1 and A2 of the rectangle will approach the point A of intersection between the vertical left-hand side of the rectangle and the horizontal boundary interface, whereas the points B1 and B2 will approach the point of intersection B in the right-hand side. As a result, the length of the straight section between the points A1 and A2 along which the field strength E is integrated tends to 0. Similarly, the straight section between the points B1 and B2 along which the field strength E is integrated, also shrinks to a point. Because the electric field E is assumed to be a finite physical quantity, the limits of the second and the fourth line integrals of the field strength along the sections of 0 length are also equal to 0. Then we only need to evaluate the first and the third line integrals on both sides of the boundary interface in this limit, which gives the following equation. The line integral of the field strength E1 at the side of the dielectric media of absolute permittivity epsilon1 along the straight section between the points A and B, plus the line integral of the field strength E2 at the side of the insulating material of absolute permittivity epsilon2 along the straight section between the points B and A, must vanish. Here the line integrals are calculated along two sections that are parallel with the boundary interface, that is we integrate the tangential components of the electric field strength on both sides of the interface. Consequently, the line integrals can be reduced to the integral of the difference between the tangential components of the electric fields E1 and E2 with respect to the distance L measured along the section connecting the points A and B. This integral is equal to 0, and for arbitrary points A and B over the flat interface the integrand must vanish. Then we conclude that the tangential components of the electric fields E1 and E2 on the two sides of the boundary interface must be equal to each other, that is the tangential components of the electric field are continuous across the boundary interface between two dissimilar dielectric materials. This matching condition can also be formulated by stating that the difference between the electric fields on the two sides of the interface must be parallel with the normal vector n to the boundary at any point of the interface, that is the cross product of the normal vector n and the vector subtraction of the electric field strength E2 from the electric field strength E1 vanishes. We already saw that for homogeneous and isotropic dielectric media the electric displacement D is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon R of the dielectric, times the electric field strength E in the dielectric. The right-hand side of this equation can also be written as the absolute permittivity epsilon of the dielectric times the field strength E. Then the matching condition of the tangential components of the electric field across the boundary interface gives the equation stating that the tangential components of the displacement D1 at the side of the dielectric of absolute permittivity epsilon1 divided by epsilon1 is equal to the tangential components of the displacement D2 at the side of the dielectric of absolute permittivity epsilon2 divided by epsilon2. In other words, the ratio of the tangential component of the displacement d1 to the tangential component of the displacement d2 is equal to the ratio of the dielectric constant epsilon1 to the dielectric constant epsilon2. This result gives another matching condition across the boundary stating that the tangential components of the displacement field are discontinuous across the boundary interface between two dissimilar dielectric materials. Here the ratio between the dielectric constants of the two dissimilar dielectrics is the measure of this discontinuity or jump in the displacement field across the interface. We saw as well that the electrostatic field E always vanishes in perfect conductors, which means its tangential component is equal to zero at the boundary surface of conducting materials. Then it follows from the matching condition for the tangential component of the electric field over the boundary surface, that the tangential component of the electric field must also vanish outside the conductor in the close vicinity of its boundary. Hence, the electric field lines always originate or terminate perpendicularly to the boundary surface of the conductor, as expected in electrostatic. Now we determine the boundary conditions imposed on the normal components of the field quantities over the boundary interface between the two dissimilar dielectric media. In order to do so, we apply the first Maxwell equation in electrostatic telling us that free electric charges are the source of the electric displacement field, that is the surface integral of the displacement field d over any closed Gaussian surface is equal to the free charge q within the surface. Since the Gaussian surface is arbitrary, we can determine the surface integral of the displacement field d over a cylinder of height h enclosing the interface between the dissimilar dielectrics with the circular bases b1 and b2 in its bottom and its top and the curved surface C. Here the circular bases of the cylinder are parallel with the plane approximating the boundary interface in the vicinity where the normal vector n is erected to the interface. Then the surface integral of the displacement d can be broken up to three surface integrals over the bases b1 and b2, and the curved surface C of the cylinder, where the surface elements ds in the integrals point outward from each surface. As in the case of the contour integral, we can also deform the Gaussian surface such that its height h tends to 0 while it will still enclose the same amount of free charges over the boundary interface. This means that the circular bases b1 and b2 approach the surface S defined by the intersection of the boundary interface and the circular surface of the cylinder with a height shrinking to 0. At the same time, the area of the curved surface C given by the product of the height h and the finite circumference of the cylinder also tends to 0. Consequently, the surface integral of the finite physical vector field d over the surface C of vanishing area is equal to 0 as the height h tends to 0, and we only need to evaluate the first and the second surface integrals on the two sides of the boundary interface in this limit. The surface element vector ds over the base surface b2 at the top of the cylinder is simply given by the normal vector n times the area element ds, whereas the same quantity for the base surface b1 at the bottom is given by the negative normal vector n times the same area element ds. As a result, the right-hand side of the equation can be written as the negative surface integral of the dot product of the displacement field d1 at the side of the dielectric medium of absolute permittivity epsilon1 and the normal vector n over the flat surface S, plus the surface integral of the dot product of the displacement field d2 at the side of the dielectric medium of absolute permittivity epsilon2 and the normal vector n over the flat surface S. This expression must be equal to the free charge q over the surface S. Then we can write that the integral of the difference between the normal components of the vector fields d2 and d1 over the area of the flat surface S is given by the free charge q over that surface. If sigma is the surface density of the free charge q distributed over the surface S, then the right-hand side of this equation can be written as the integral of the surface charge density sigma over the area of the surface S. Because the choice of the cylinder, that is the surface S of its intersection with the plane approximating the boundary interface in a small vicinity is arbitrary, the integrands in the two sides of the equations must be equal to each other. Then we conclude that the difference between the normal components of the electric displacement fields d2 and d1 on the opposite sides of the boundary interface must be equal to the surface charge density sigma over the interface, that is the normal components of the displacement field are discontinuous across the boundary interface between two dissimilar dielectric materials, and the surface charge density is the measure of this discontinuity or jump in the displacement field across the interface. Evidently, without any free charge on the boundary interface, that is when the surface charge density over the interface vanishes, the normal components of the displacement field become continuous across the boundary interface. This matching condition can also be formulated by stating that the dot product of the normal vector n to the boundary interface at any point and the vector subtraction of the displacement field d1 from the displacement field d2 at that point is equal to the surface charge density sigma at that point. For homogeneous and isotropic dielectric media we can apply the relationship between the displacement vector and the electric field strength again, stating that the displacement d is equal to the absolute permittivity of the corresponding dielectric times the field strength E. Then the boundary condition gives an equation stating that the absolute dielectric constant epsilon 2 times the normal component of the field strength E2, minus the absolute dielectric constant epsilon 1 times the normal component of the field strength E1, is equal to the surface charge density sigma. This results indicates that the normal components of the electric field are also discontinuous across the boundary interface in the general case. If the two dielectric media with different dielectric constant are perfect insulators, then there is usually no free electric charge at the interface between them that can be transported from somewhere else. As already stated, for a vanishing surface density sigma of free charges over the boundary interface, the normal components of the displacement are continuous across the interface. Hence, the absolute dielectric constant epsilon 1 times the normal component of the field strength E1 is equal to the absolute dielectric constant epsilon 2 times the normal component of the field strength E2. Consequently, the ratio of the normal component of the field strength E1 to the normal component of the field strength E2 is given by the ratio of the absolute permittivity epsilon 2 to the absolute permittivity epsilon 1. This means that the normal components of the electric field are always discontinuous across the interface between dissimilar dielectrics, regardless of the presence of free charges over the interface. As in the case of the tangential components of the displacement field, the ratio of the dielectric constants of the two media is the measure of the discontinuity or the jump between the normal components of the electric field across the boundary interface. If there are free charges at the interface, the condition for the discontinuity also depends on the surface charge density sigma over the interface. As already mentioned in the case of the boundary condition imposed on the tangential component of the electric field field vanishes inside a perfect conductor. If we suppose that one of the media separated by the boundary interface is a perfect conductor, for example the one with the dielectric constant epsilon 1, then both the normal and the tangential components of the electric field are equal to 0 within that material. The matching condition tells us that the normal component of the electric field E1 is given by the ratio of epsilon 2 to epsilon 1, times the normal component of the electric field E2 outside the conductor. Here the normal component of the field E1 inside the conductor vanishes. Since the field lines of the electric field in the dielectric medium are perpendicular to the surface of the conductor, its normal component is a finite non-zero quantity. Then the product in the right-hand side of the equation is equal to 0 only if the ratio of the dielectric constants vanishes. The absolute permittivity epsilon 2 of the insulating material outside the conductor is a finite non-zero quantity, and the ratio will vanish if the dielectric constant epsilon 1 is infinite. Therefore, in electrostatics perfect or ideal conductors are often treated as dielectric materials with infinite permittivity. After determining the matching conditions all the components of the field strength and the displacement field we summarize the results in the general case. The boundary conditions imposed on the field quantities across a boundary interface of an arbitrary shape between two homogeneous and isotropic dielectric media at any point on the interface with free surface charges gives the following set of equations. The first equation states that the projection of the discontinuity between the displacement fields d1 and d2 across the interface to the local normal n to the interface is given by the local surface density sigma of free charges over the interface. That is, the displacement field is only continuous in the normal direction if no free charges are present over the interface. The second equation is the consequence of the first one where the displacement field is expressed in terms of the absolute permittivities epsilon 1 and epsilon 2 of the two dielectric materials and the field strengths E1 and E2 in them. This condition shows that the electric field always have a discontinuity in the normal direction with respect to the boundary interface, even if the surface density sigma of free charges vanishes over the interface. The discontinuity is determined by the dielectric constants of the two media, and the surface charge density sigma if free charges are present. Both of these equations impose constraints only on the normal components of the electric field strength and the displacement field, and we need other two equations for the boundary conditions of the tangential components of the field quantities. The third equation states that the electric field is always continuous across the boundary interface in the tangential direction with respect to the interface, as the vanishing cross product indicates that the discontinuity in the electric fields E1 and E2 is parallel with the normal vector n. For the last equation we express the vectors of the field strength in terms of the dielectric constants epsilon 1 and epsilon 2 and the displacement fields d1 and d2 in the third equation. As a result, we obtain a condition for the displacement field stating that it is always a discontinuity in the tangential direction with respect to the boundary interface. The jump in the tangential components across the interface depends on the ratio of the dielectric constants of the two media. This is the second set of boundary conditions imposed on the tangential components of the field strength and the displacement field across the boundary interface between two dissimilar dielectrics. As already discussed, these conditions are still valid if one of the media is a perfect conductor with an infinite dielectric constant. They also hold for a vacuum, where the absolute dielectric constant can be reduced to the vacuum permittivity on the side of the boundary where the space is empty. However, these boundary conditions are the consequence of the Maxwell equations describing the field quantities in electrostatics. If the electric field is time-dependent, then the same conditions must be derived from the full set of the time-dependent Maxwell equations describing the time evolution of the complete electromagnetic field in the two media separated with the boundary interface. It involves some modifications of the original equations due to the time evolution of the electric field generating a magnetic field. The equations derived for the electric field must also be supplemented with the equations of the boundary conditions for the quantities describing the magnetic field. As the consequence of the boundary conditions imposed on the field quantities across the boundary interface between two dissimilar dielectrics, we can prove the law of refraction for the field lines of the electric field and the displacement field at the interface. For the electric fields E1 and E2 at the boundary interface between the insulating media with the dielectric constants epsilon1 and epsilon2, let θ1 and θ2 denote the angles between the vectors of the electric field and the normal vector n to the interface. Then we have the following trigonometric relationships between the angles and the components of the electric field strength. The tangent of the angle θ1 is equal to the ratio of the tangential component of the electric field strength E1 to its normal component. Similarly, the tangent of the angle θ2 is given by the ratio of the tangential component of the electric field strength E2 to its normal component. For the linear dielectric materials considered here, the displacement field is proportional to the electric field strength, where the constant of proportion is the absolute dielectric constant of the medium. As a result, the electric field strength and the displacement field point in the same direction at any point of the dielectric media, and their components with respect to the normal vector have the same directions as well. Hence, the tangent of the angle θ1 can also be written as the ratio of the tangential component of the electric displacement field d1 to its normal component. Similarly, the tangent of the angle θ2 is equal to the ratio of the tangential component of the electric displacement field d2 to its normal component. As already seen, the boundary conditions derived for the field quantities with respect to the local orientation of the boundary interface between the two media provides the following relationships for the components of the field quantities in the media. The tangential components of the electric field strengths E1 and E2 are equal to each other across the interface, whereas the ratio between the tangential components of the displacement vectors d1 and d2 across the interface is given by the ratio of the absolute permittivity epsilon1 to the absolute permittivity epsilon2. For the normal components we obtain the following equations. The difference between the normal components of the displacement vectors d2 and d1 across the interface is equal to the surface density sigma of the free charges over the interface. Similarly, the difference between the product of the dielectric constant epsilon2 and the normal component of the field strength E2, and the product of the dielectric constant epsilon1 and the normal component of the field strength E1 across the interface, is given by the surface charge density sigma. Here we restrict our attention to the case where there are no free charges over the boundary interface, that is when the electric surface charge density sigma vanishes. Then we can reduce the boundary condition for the normal components of the displacement to the equation stating that the normal components of the displacement fields d1 and d2 are equal to each other across the interface. Similarly, the boundary condition for the normal components of the electric field strength will tell us that the ratio between the normal components of the field strengths E1 and E2 across the interface is given by the ratio of the absolute permittivity epsilon2 to the absolute permittivity epsilon1. By considering the trigonometric equations written for the angles θ1 and θ2, we can express the ratio of tangent θ1 to tangent θ2 as the ratio of the tangential component of the field strength E1 to its normal component, times the ratio of the normal component of the field strength E2 to its tangential component. If we apply the first boundary condition in the right-hand side of this equation, then we can reduce it to the ratio between the normal components of the field strengths E2 and E1. Now we use the fourth boundary condition, which gives the ratio of the dielectric constant epsilon1 to the dielectric constant epsilon2. We will obtain the same result for the displacement fields, if we express tangent θ1 over tangent θ2 as the ratio of the tangential component of the displacement vector d1 to its normal component, times the ratio of the normal component of the displacement vector d2 to its tangential component. Now we can use the third boundary condition in the right-hand side of the equation, which gives the ratio between the tangential components of the displacement vectors d1 and d2. Then we apply the second boundary condition and obtain epsilon 1 over epsilon 2, as in the case of the electric field strength. As a result, we have established the law of refraction for the field quantities at the boundary interface between two dissimilar but homogeneous and isotropic dielectric media, stating that the tangent of the angle θ1 between the normal to the interface and the direction of the electric field and the displacement field in the medium with the absolute permittivity epsilon 1, divided by the tangent of the angle θ2 between the normal to the interface and the direction of the field quantities in the medium with the absolute permittivity epsilon 2, is equal to the ratio of the dielectric constant epsilon 1 to the dielectric constant epsilon 2. The law of refraction tells us when an electric field and electric displacement cross an interface from a medium with lower permittivity to a medium with higher permittivity than the angle with the normal increases, that is, the field lines bend away from the normal to the boundary interface. Consequently, the density of the field lines is greater in the medium with higher permittivity. This situation is illustrated in the figure with a homogeneous and isotropic dielectric slab with the absolute permittivity epsilon 2 introduced into a uniform electric field E, where the media surrounding the slab has a dielectric constant epsilon 1 that is less than epsilon 2. This effect can also be studied well if a ring-shaped dielectric with a high dielectric constant is placed in an electric field. Due to the refraction of the electric field lines, most of the lines of force are concentrated in the wall of the dielectric ring, and the density of the field lines becomes less in the space enclosed by the ring. The dielectric ring thus exerts a shielding effect similar to metal cavities. The shielding effect will not be perfect, but the greater the permittivity of the dielectric, the stronger the shielding effect. Evidently, only conductors which are considered as dielectric materials with infinite permittivity can produce perfect electric shielding.